Now that we've been introduced to polar coordinates, we know where to find them on the polar plane. Here comes the good stuff, the graphs of these polar functions. So you got a couple of options when you make a polar graph. One of them is simply to do inputs, outputs. Like, how did you first learn to graph a line? Somebody said, let's make a t-chart. And they made a little t-chart, and they gave you a bunch of x values, and you put them into the equation. You got a bunch of y values, and you plotted the points, and you made a line. And then you made a parabola, and then you made a cubic function, and eventually you made a sine curve. Well, you could do the same thing with polars, right? You could take a bunch of theta values, throw it into the equation, and find the radius, and then graph them in terms of r theta. Another way to do it is to look at the original function in rectangular form and see how the polar function matches up. And I like that method better because unless you have some idea what these functions do in terms of r's and thetas, it's going to be tough to graph them accurately because you're going to get a bunch of points on the plane. But as you'll notice when you do these, not all of them connect directly the way we think they do. And so I mentioned a couple of things that we can do, right? We can input angle measures and output radii. You can also look at the corresponding graphs in rectangular form, which is what I'm going to do. So let's see how I do this on a screen. I've done this many times on a gigantic whiteboard, but let's see how this works on a little whiteboard screen. So my graph that I want to graph is r equals 7 minus 7 sine theta. Well, this corresponds to y equals negative 7 sine x plus 7, right? So if I replace the r with a y, and I replace the theta with an x, I get 7 minus 7 sine x. I flipped it around because you're more used to seeing the sine first and then the vertical shift at the end. So let's think back a couple of chapters to see what negative 7 sine x plus 7 looks like. So maybe I just start with plain old sine x. Sine x starts like this, starts the origin, goes up, down, back up again. Okay. If I put a negative in front of the sine x, what does a negative in front of the sine x do? It flips it, makes it go down, up, and back down again. Starting at 1, going down to negative 1. Well, now, instead of multiplying it by negative 1, what if I multiplied by negative 7? Well, here, I'll make that go up to 7 and down to negative 7. So that's what y equals negative 7 sine x looks like. The plus 7 here at the end is going to push that up 7 units. So when I push this up 7 units, y equals negative 7 sine x plus 7 is going to look like this. Instead of having a midline at 0, it's going to have a midline at 7. It's going to go up to a max of 14, and it's going to come down to the axis. So it's going to go down, up, and back down again. Okay. What are the important points on this graph? Well, it used to cross the axis here at pi, so it's going to cross here at pi. It's going to hit its minimum at pi over 2. It's going to hit its maximum at 3 pi over 2, and it's going to end at 2 pi. So from this graph, I'd like to get some information about the radius of my new function. Well, what I've graphed actually is the radius. So when theta is 0, right? Theta is 0 here. When theta is 0, the radius is 7. I know that because it starts here at 7 at theta equals 0. Then the radius decreases. It decreases to 0 on the interval from 0 to pi over 2. Right? And we see it in that first quadrant. Here, to change colors. We see it decreasing here from 0 to pi over 2, right? In this region here, the radius is decreasing. Then what does it do? It begins to increase again. So it increases back to 7 on the interval from pi over 2 to pi. Oh, but then it keeps going, right? It goes all the way up to 14. So the radius increases to 14 from pi to 3 pi over 2. And then it comes back down again. The radius decreases to 7 on the interval from 3 pi over 2 to 2 pi. Okay, so how does this translate into the graph of a polar curve? All right, here, let's do this. I took the directions over here and I copied them onto the next slide because I'm not going to be able to draw a nice straight picture over there. So here are the directions from the last page. I'm going to graph it over here now so we can see what this looks like. First of all, we need a set of axes. So, best as we can, I'm not going to draw the whole polar graph paper because we can do this in rectangular form. It says theta equals 0 when the radius is 7. So here's theta equals 0. Now, what does a radius of 7 look like? Well, it's 7 units from the center. We have to pick an appropriate color to graph this with, so I'll graph it in red. Right, so here's theta equals 7. Now, if the radius stayed the same, then I would create a quarter circle from 0 to pi over 2, right? Think of the spokes of a bicycle wheel. All the radii would be 7. Every one of them would be 7 here and here and here and here and here, all the way till I got back down there. But the radius is not 7 all the way through. The radius decreases. So think of taking those spokes of the bicycle wheel and pulling them in. What would happen? It says the radius decreases to 0 by the time I get to pi over 2. So by the time I get up there to pi over 2, the radius is 0. Then it says the radius begins to increase again until it gets to pi. Well, here it is at pi. It says the radius increases to 7, but it increases to 7 in the direction of pi, which we might call negative 7. Those are really not symmetric. Okay. Now it says the radius increases to 14, but in the direction of 3 pi over 2. So I'm going to need a little bit bigger axis for this. Direction of 3 pi over 2 is down. Right? So there's 3 pi over 2. I'm going 14 in the direction of 3 pi over 2. So 14 in the direction of 3 pi over 2 is down here, right? That's negative 14. So this graph comes around. And then it says it goes back to 7 by the time it gets to theta equals 0. Now, I'm drawing this on a tablet, not very well. But it has an appearance like this. And each of these has a name. They get easy at the beginning. They get harder as we go further along. This one, if I had drawn this nice and symmetric, should look like a heart. And in fact, it is called a cardioid. All right? Cardioids obviously look like hearts. That's where they get their name from, cardiac. But there's other uses for cardioids as well. This microphone that I'm using to record these lecture videos is a cardioid microphone. Now, if you do any kind of sound system setups, you know what a cardioid mic is. A cardioid microphone has a pickup pattern that looks like a cardioid, meaning that if you stuck a microphone in the middle of a stage or something and you wanted to pick up everything on that stage, you wouldn't want this pattern. You would want a pickup pattern that's circular, that picks up everything. So from the center of the microphone, it picks up everything in front and behind it. But if you're a singer on the stage and a pickup pattern looks like that, you're going to pick up the drums and the guitars and the bass and everything else behind you, and the guy running the soundboard isn't going to have any control over your voice. So you want one that blocks out the sound behind you and only picks up the sound in front of you. So if you're standing here, you want the microphone to pick up what's coming out of your mouth and not the stuff on the other side of the microphone, which includes the crowd noise, by the way, too. Same thing with broadcasting. If you're broadcasting a baseball game, maybe you do want some crowd noise in the background, but you probably don't want so much that they can't hear you over the crowd noise. And so you would want a microphone with a pickup pattern that looks like this. On the other hand, if you're just throwing a mic on stage for like second graders to sing a song at a parent performance or something like that, don't use a microphone like this. Otherwise, the other half of the stage isn't going to get picked up. You only get the ones that are right in front of the microphone. So cardioid pickup patterns for microphones are one example of why we would have a graph that looks like this. All right, let's take a look at this one. R equals 3 cosine 2 theta. What does 3 cosine 2x look like? Well, cosine of x looks like this, right? It starts here, goes down, and back up again. And normally it would do that from negative 1 to 1, but this one is 3, so it's from negative 3 to 3. The other thing is we can fit two of those from 0 to 2 pi, so this only goes really from 0 to pi. This here is pi over 2, and this thing now is pi over 4. Pi over 4, 3 pi over 4. So the radius is 3 when theta is 0. Then the radius decreases to 0 on the interval from 0 to pi over 4. Then it decreases to negative 3 from pi over 4 to pi over 2. Then it begins increasing again. It increases back to 0 on the interval from pi over 2 to 3 pi over 4. And then again until it gets to pi. So it increases to 3 on the interval from 3 pi over 4 to pi. Now, the good news is once we've done this once, we just rinse and repeat, because it'll do the same thing from pi to 5 pi over 4, 5 pi over 4 to 6 pi over 4, which is 3 pi over 2, 3 pi over 2 to 7 pi over 4, and then 7 pi over 4 to 2 pi. One question that comes up sometimes is, do we really need all of these? Like, do we need to go again from pi to 5 pi over 4, 5 pi over 4 to 3 pi over 2, etc.? We'll find out in a second. All right, so let's pick it up on this side here. The set of axes, so let's make ourselves a set of axes. The radius is 3 when theta equals 0. So here when theta equals 0, the radius is 3. Decreases until it gets to pi over 4. So here's pi over 4, right? Halfway in between. So it gets back to 0 by the time it gets to pi over 4. Now it gets a little funky, right? It says it decreases to negative 3 from pi over 4 to pi over 2. Well, pi over 4 to pi over 2 is this region in here. If it's negative, it must correspond to the reflection down here. So when it says it goes to negative 3 in the direction of pi over 2, negative 3 in the direction of pi over 2 is down here. Then it goes back to 0. And then it goes to 3 in the direction of pi. So 3 in the direction of pi is really negative 3. And that might answer one of our questions is, do we need the second half of it? Yes, we do, because otherwise we have a really weird looking graph. So let's try to find the second half of this thing. So the radius decreases back to 0, okay, until it gets to 5 pi over 4. Then it goes to negative 3 in the direction of 3 pi over 2. Well, this is the direction of 3 pi over 2, so the opposite would actually end up being up here. Then it comes back to 0. Then it goes back to 3. So what is this? It's not a fan blade, although it kind of looks like a fan. Airplane propeller? No. It's a rose. And there's all different kinds of things we can get out of this, right? This equation that we had was r equals 3 cosine 2 theta. So obviously the 3 impacts how long the petals of the rose are. This number here, that 2 before the theta, impacts the number of petals. So if that number is even, you're going to get twice as many petals. If that number is odd, you'll get that many petals. So if you did 3 cosine of 4 theta, you would get 8 petals. We did 2 theta, so we got 4 petals. And if I had done 3 cosine of 3 theta, we'd have 3 petals. The difference between cosine and sine impacts where those petals are. So that if I did 3 sine of 2 theta, I would get the petals in between 0 and pi, 0 and pi over 2, and pi, etc. All right. The other two can be graphed the same way. This one is a little funky. R equals 2 minus 4 sine theta. And that's because what happens when we graph negative 4 sine of x plus 2? When we do negative 4 sine of x plus 2, instead of it going from 0 to 1 and 0 to negative 1, it would go from negative 4 to 4. But then it's also negative, so it goes underneath. So it comes down here and back up again. That being 4, that being negative 4. But the plus 2 at the end doesn't clear the axis. Remember when we did that first graph? When we pushed it up, it cleared the axis and it only touched that one point at pi over 2. This one's not going to do that. When I push this up, it's only going to go up 2 units, which means the midline is going to be at 2. This thing is going to come down, cross the axis, go up, and back down again. So the max is now at 6. The minimum's at -2, and this has a couple intercepts that it didn't have before. Rather than go through the whole thing, I'll give you some values. This is pi. The two intercepts here and here are pi over 6 and 5 pi over 6. So the short version of this story is this. What the graph does, and I got to switch to an appropriate color to do this, is that it starts with a radius of 2 at theta equals 0, comes back to the pole by pi over 6, then goes to -2 by the time it gets to pi over 2, so -2 is down here, comes back to the origin at pi over 6, and by pi it has a radius of -2, which now is looking like the graph that we graphed before, except for this piece over here. Now, by the time it gets to 3 pi over 2, it has a radius of 6, so it actually comes and loops back around itself and up to the other side. I'm just going to tell you what this is. It's called a Limacon, where it looks like the word Limacon, because this piece in the middle here is supposed to remind you of a lima bean. So that's what they call it, a Limacon, or a Limacon as it's written. And the reason that it has that extra loop inside of it that a cardioid and a circle don't is because of this piece down here. And if you wrote out all the increasing, decreasing stuff, you would see it loops, and then it loops back around itself to get to that radius of 6. The first graph that we graphed, we pushed it up far enough that it cleared that axis, and we didn't have to worry about it. All right, let's look at one more by hand, and then I'll graph a couple of other ones, and we'll wrap this up. R squared equals 5 cosine 2 theta has a little twist to it, which is, what if I was kind of cheap and I took the square root of both sides? Little hand waving involved here. But a square root of 5, I'm going to, again with a little hand waving, say that the cosine of 2 theta, if I take the square root of it, is not going to make a drastic difference in many places because I'm only going between -1 and 1, or let's say between 0 and 1. So cosine 2 theta, going to look like this from 0 to pi, and then it's going to repeat from pi to 2 pi. So nice and easy, right? That's pi over 2, pi over 4, 3 pi over 4. Here's our challenge. The graph says the equation says r squared equals 5 cosine 2 theta. Well, r squared doesn't exist down here, which means the graph doesn't exist between pi over 4 and 3 pi over 4. So the radius is the square root of 5. It goes down to 0 by the time it gets to pi over 4. But then it simply doesn't exist between pi over 4 and 3 pi over 4. It picks up again and goes to a radius of square root of 5 in this direction. Then it repeats. It comes back down to the pole. But then between 5 pi over 4 and 7 pi over 4, again, this graph is below the axis and it doesn't exist. Then from 7 pi over 4 to 2 pi, it comes back again like that. So the pieces in between are not pieces that are looped around. The pieces in between are places where the graph actually doesn't exist because the r squared value can't be negative. All right, looks like an infinity sign, a belt, Mobius strip. It's actually called a lemniscate. Lemniscate comes from an ancient word that means to decorate with ribbons, and so this is supposed to remind you of decorating with ribbons. Maybe it does, maybe it doesn't. But that's what the intention was. All right, let's wrap this up with me showing you a couple of things of graphs that I am not going to graph by hand. So these last two things on here, one is called the Archimedes spiral, and the other is called a logarithmic spiral. So let's see what each one does. I pull up Desmos here, and you can graph things in rectangular form on Desmos. R equals 1 plus 2, and for theta, I'm going to type in theta. Look at that. Now, if I zoom out, that's my Archimedes spiral. You notice down the bottom it asks me to give values from 0 to 12 pi. Okay. What if I narrow that down? What if I went -4 pi to 4 pi? Ooh, that's a funny looking thing. Let's graph these separately. So there it is from 0 to 12 pi. Here it is from negative 12 pi to 0. So the red one, or the blue one is the original one, right? 0 to 12 pi. I have to widen my screen a little bit here. Right? That's the part from 0 to 12 pi. Switch it around. This is the part from negative 12 pi to 0. Combine them together, and you got a really funky-looking Archimedes spiral. All right? So it meets in the middle, turns around, and goes the other direction. All right, let's try the log spiral. R equals log theta. Ooh, this does not look at all like the other one. Very different viewing window. Instead of going from like negative 60 to 60 or whatever that last one was, notice that this one doesn't go very far. We're talking about logs. So the log of 100 is only 2. And so 12 pi is about, what, 37, 38? So we're not even near 2 yet. It comes around here, makes a loop. And then you notice that these spirals get closer and closer to each other, because that's what happens when you take logs of numbers. The other one was just 2 theta, so they stayed equal distance apart. This one is a log of theta. So for a log of theta, the more theta values you put in, the more the closer they're going to get. So if you want to go from 0 to, let's say, 100, you notice now it goes all the way out to 2, because the log of 100 is equal to 2. But again, because it's a log function, those spirals end up getting closer and closer and closer until you get to 2. Now, if you want to make that go out to 3, you're going to have to make it go out to theta equals 1,000. That's going to be a pretty dense-looking graph. Right? It gets so dense that Desmos can't even separate it anymore. So that's what it looks like when it goes out to 1,000. Right? There it is going out to 100. So the Archimedes spiral, the logarithmic spiral, those are things we're not going to graph by hand, but it is kind of cool. And clearly, it would be tough to graph these in rectangular form. And that's part of the point of this, is that polar coordinates allow us to create graphs of things that we would either find very challenging to graph in rectangular form, or that would be almost impossible to graph in rectangular form. And they will be functions in polar form, but as you can see by looking at this, in rectangular form, this would not be considered a function. So hopefully this gives you a nice idea of some ways that we can graph these polar coordinate functions and the cool graphs that come out of them.